CFTs.
Thank you everybody for being here. Okay, so we have been introduced to 2D chiral CFTs a couple of times before, earlier this week, and we've also been told that there are essentially various mathematical axiotizations that are equivalent in some ways. So there is, let me try it. There are VOAs, there's conformal nets, and there are functorial approaches, which is like representations of some kinds of cobordism categories. And this is also what Siegel first told us is the modular functor. And if you start with a vertex operator algebra, you can build a representation category. And if your vertex algebra was nice, let's say rational, then this category that you get happens to have really nice properties, that it happens to be a modular tensor category. And then you can go on and try to build this modular functor from the data of conformal blocks from this vertex operator algebra. So people who do algebraic geometric approaches to VOAs have made a lot of progress in this. And then the second approach is of conformal nets. Brandon mentioned yesterday to us that conformal nets help us prove things, which will be visible later during the talk, but because I don't want to assume people know what it is, so I'll briefly mention. So the data of the net is a Hilbert space, which is the vacuum sector, a pointing, which is the vacuum vector. There's a strongly continuous projective representation of diff S1. And most important part of the data is that there is an algebra, which is a Warman algebra A of I, represented on this vacuum Hilbert space, and for every interval on the circle S1. And conformal net is essentially capturing the AQFT approach, like the AQFT data or the algebraic quantum field theory data for left movers or right movers for a 2D CFT. And the data, the conditions that this data has to satisfy is isotony and locality, which people who do physics are very familiar with. Then there is a covariance condition for this action of diff S1 we have. There's the positivity of energy condition saying that the generator for rotations has to have a positive spectrum. And lastly, there's a condition on the vacuum vector that it is the unique vector that is spanned by the Mobius group, and it is cyclic for the algebra generated by all the algebras assigned to different intervals. So cyclic just means that it creates a dense image. So if I act with this algebra on omega, I get something dense in H0. Yes.
So you talk to a VOA person.
Yeah.
If you say the word unitary, they'll look at you like you're crazy. But somehow for a conformal net, if you
Yeah.
looked at
Absolutely. So that is literally how I will. So there's no notion of nets for non-unitary, yes, like chiral CFTs yet. Some people in Australia are trying. I can tell you the names of them later. But it's hard. Okay, so if you have a unitary vertex operator algebra, then these people wrote a very remarkable paper, which is called From VOAs to Conformal Nets and Back. So given a unitary VOA, you can construct a conformal net. Essentially, the way you think about it is you pick up a test function f, which is localized or supported in your interval I, and you smear your operator with this. So this YAF is a smeared vertex operator. And to go back, so if I put enough, oh my God. Okay. If I put enough adjectives on VOAs and conformal net, I can, okay. Stop play. X the little box. Sorry. Oh. Okay, and then James Senner and Andre Enriquez in 25 wrote a backwards paper, which they said, given any conformal net, you get a unitary VOA. So this is kind of the state of affairs right now. With the paper in 2018, there was some overlap with James and Andre's work. You can, any conformal net gives you a unitary VOA, and conjecturally they are equal. Okay, so for chiral functorial CFT approach, it has to be a functor out of a Watson category to some target, which I'm right now just calling 2v for some higher vector, vect in some sense. And it's a relative theory, so there is a functor called z of chi top, and there's a natural transformation of pointing, which I call z of chi holomorphic. And if you stare at this and the extra data on the annulus and the extension, I will not talk about right now. So the part in yellow is what I will focus on for the definition. For a given closed one manifold, this data amounts to assigning some algebra, and it can be a topological algebra of your favorite flavor. For a complex cobordism, you will assign a bimodule with a pointing, and the axioms dictate that the bimodule that you assigned is only topologically dependent on sigma, and the pointing actually is holomorphically dependent. So this is kind of hidden in different parts of the definition that I've not said, but there are axioms that dictate that. Okay, so what I want to do now is to fully extend this definition essentially, because chiral CFTs are closely associated with 3D TFTs, and TFTs we know like to be fully extended. So if I want to extend this, I need to come up with a better target. And what we know for targets essentially is that if I take the loops at the monoidal unit of my target, I should get one category level lower. So whatever I want to call 2-vec, if I look for the monoidal unit and take the endomorphisms of it, I should get vec. And if I'm purely algebraic, the Morita theory gives you a nice way to do it. So you can take associative algebra objects in V and take the Morita and then recover higher vector spaces, essentially. So here I take vec, plug in vec, take E1 objects in vec, that gives me alg. I take the Morita category, that is the category of algebras, bimodule maps. And I can take rep of this thing and get the two category of lincats for nice enough things. And now I can plug in lincat again into this machine and get tenscat, and so on. I can keep doing it. Especially if I am really interested in TFTs and want to be fully dualizable, the higher Morita theory is very well developed. And just to point out, the composition of one morphism in this category is just the fusion of modules, and identity is just the algebra itself. And similarly for tensor categories, this is the Boolean tensor product, and the identity is again the category as a bimodule over itself. Okay, so I'm going to just highlight some very basic constructions in the algebra land. So if I have a vector space, I can take its endomorphisms and recover an algebra. And if I have an algebra, I can forget that it was an algebra and have a vector space again. And similarly for tensor categories and linear categories. There are some other things I can do. If I have an algebra, I can take its bimodule categories and it will be a tensor category. And given a tensor category and an object in it, I can recover an algebra by taking the endomorphism. On the left-hand side, if I have a linear category, that by definition means it's vector rich. So I can take two objects, take the hom, and get vec. And if I take the category of all vector spaces, it's a linear category. Don't think I'm kind of boring you, but the point is, if I want to replace vector spaces by Hilbert spaces now, there are lots of things that go missing. So firstly, the underlying space of a von Neumann algebra is not a Hilbert space. So there is a question mark there. And whatever is the analog of linear categories in this world is not Hilbert-enriched. So that part is broken. And of course, then in the tensor category land, if I have function analytic tensor categories, they're expected to be not be modules over themselves as function analytic objects. So first, I would want to tell you what this thing, which was here as complete W star categories was. So these are function analytic linear categories. And they essentially are von Neumann algebroids. So if you want to think of a linear category as an algebroid such that every object has an endomorphism algebra, here every object has an endomorphism von Neumann algebra. And the inner product of the Hilbert spaces has a direct analog there. Instead of a complex valued inner product, you have a Hill valued inner product. If there is an analog of the Rhesus representation theorem, and every functor between two such categories admits an adjoint. And this is not the categorical adjoint. This is really a function analytic adjoint and has no assumptions on categories being finite, semi-simple, or anything like that. So this really is like a categorification of Hilbert spaces. Okay, so the first part there, given a von Neumann algebra, since the 70s, we know how to make a canonical Hilbert space. There is something called the standard form, which is L2 of A. And a key point to notice is that this thing is canonical, but there is no universal construction. And then similarly, one of the vertical arrows given a complete W star category, I wanted to recover a Hilbert space. I told you that the form is not Hilbert rich, it's only Banach enriched. So there is a trick to do that. So you take your home of x plus y essentially, and then you now this is the von Neumann algebra. And now you can take the L2 of this, which gives you a Hilbert space, and now you take a corner of it. So a priori, if I had only taken home xy, it would not have been enough. But if I take a corner after making it a Hilbert space, it happens to be good enough. And for the lower thing, there's an analogy. So the kind of von Neumann algebras that we have seen and loved are like bounded linear operators on Hilbert spaces. So things like B of H. And we know that L2 of B of H is what is called the Hilbert-Schmidt maps. And Hilbert-Schmidt maps are a two-sided star ideal. So if you tensor something with a Hilbert-Schmidt operator, you get a Hilbert-Schmidt operator again. And this is kind of the intuition of how we will generalize this L2 construction. So we'll ask for something called the absorbing ideal of our tensor category. And these are objects such that omega tensor x is omega and x tensor omega is omega for any object x. So if you think, oh my god, such objects might not exist, think of Hilb as your category, and the canonical infinite dimensional separable Hilbert space is in particular an object like that. So, okay. And I'm basically trying to list all the things that are kind of broken in the function analytic land. So a von Neumann algebra, this category Vn alg by mod. I showed you for alg by mod, you could have taken two modules and taken your universal property of tensor products and constructed a new module by tensoring over the algebra. But it happens so that if you have von Neumann algebras and you try to do something like that, you don't recover what you want, and you don't recover a Hilbert space in particular. So what you have to do is called confusion, and it was developed by Alison in the context of trying to fuse representations of loop groups. And so it's the completion of a vector space, which is this vector space I have written, form B linear from L to B to H, then tensor over L to B, and then form B linear again from L to B to K. And there's a canonical inner product that you can write on it. And when you complete this vector space with respect to this, you can show that this satisfies nice properties. So, for example, L2A behaves as the unit for this process, and it is associative and so on. And now if I'm going to categorify von Neumann algebras, I will have to categorify this process of fusion of its modules. And you can imagine it looks ugly, and it was ugly, and spoiler alert, just trying to categorify this did not work, but something else worked. Okay, so here is how I try to categorify von Neumann algebras first. So given a C linear algebra, I can have a C linear monoidal category. So algebra just becomes a monoidal category. A star algebra becomes what is called a bi-involutive, or in other words, a fully daggered category. So there are two involutions present. one at the level of objects and one at the level of morphisms. Think of the category hill. There is obviously a dagger of linear maps, which is this dagger 1. But there's also something else you can do on the level of objects, which is take the complex conjugate. And there is this dagger 0. And this biinvolutive structure is the categorification of the star structure. So there happens to be two levels of dagger that start appearing. And if I want to now define the commutant, so the way one-Neumann algebras are defined, you say they are double commutant closed. So I have to define commutant of an algebra inside another algebra. And this is also well developed in the theory of tensor categories. So given a tensor functor between two categories, I can create its relative center. And if this functor was identity, this process would have recovered the Drinfeld center. So this is kind of a generalization of the Drinfeld center, which gives you objects of the target category with some half-braiding data. And this L2A will be replaced by what I told you was the absorbing ideal. So this absorbing ideal is generally a non-unital monoidal complete W star category. And now I will try to convince you that this bicommutant property of one-Neumann algebras can be stated for tensor categories of this flavor. Okay, so if I take T to be a complete biinvolutive W star tensor category that admits absorbing objects, I have two functors, the left and the right multiplication. So if I take an object of my tensor category and tensor it with an absorbing object, I told you that we'll get an absorbing object. So this is an endofunctor for T abs. And similarly, the right multiplication is an endofunctor. And what we want to do is make these two functors into appropriately higher dagger functors. So that involves supplying some extra structural maps. So there are these structural maps which say that if I input the bar of my object, then I should recover the dagger of the functor. So dagger is the involution at the level of objects in this target category and TABs. So this structure map is essentially making these two functors compatible with the dagger structures. And the property we want to check is that there are comparison maps from T to the relative center of R and T monoidal off to the relative center L. And we want to say that these is the equivalence of categories, these two maps. And then there are lots of coherences for the data. This would have been analogous to if somebody wanted to define one-Neumann algebras as star algebras that admit a canonical Hilbert space such that the left and the right action on this Hilbert space are each other's commutants. And this idea was actually hidden in Graham Siegel's, one of his notes that he never published called the locality of QFT. So he really disliked function analytic things and did not want to do one-Neumann algebras, but he noticed that this bicommutant property, that the left action is the commutant of the right action, is kind of the key that was holding things up. So it's nice that we can categorify this easily. Okay. Now, the confusion process. I showed you a very ugly formula of completion of a vector space with respect to some inner product. So the first couple of years, I was trying to write a formula that was a categorical analog of that. But what we don't know is how to complete with respect to an inner product at the level of categories. There were some ideas as to maybe you can put some lattice of sub-objects and complete with respect to that, but nothing worked out. But then there was a happy accident that there was another formulation for this inner product. So what you can do is if I have H and K, where H was the right K, A module and K was the left K, A module, I could take H bar plus K, and now they're both left A modules. I take the endomorphisms in A mod, and now this is a one-Neumann algebra. And I can take the L2 of it, and now again I do this project into the corner. And this happens to be isomorphic to the previous definition I showed you of the confusion product. In principle, if these H and K were Hilbert spaces and I replace A by just C complex numbers, I would recover the tensor product of Hilbert spaces with this formula. And this I can just go ahead and write and replace H and K by now module categories M and N over my function analytic tensor category, and replace L2 by abs and just hope and pray that this works. And now this was all designed so that I could have a 3 categorical analog of tens cat, because one of the reasons is that we know that to the circle for Reshtick derived theories and for chiral CFTs, we want to assign something like representation category of the VOA. And even in nice cases when this category is an MTC, there does not exist a fusion category whose Drinfeld center is that category. So that was kind of a hint of why you needed to expand your world and enter the function analytic land, because now you can find a category whose Drinfeld center is going to be the representation category without any assumptions on rationality in particular. So to do this process, to construct a fully extended functorial chiral CFT, to a point, I will assign a bicomutant category or a categorified one-Neumann algebra or a function analytic tensor category, whatever word is more palatable to you. And to a one manifold, I will assign some bimodule categories, and to two manifolds, you would in principle assign bilinear or equivariant functors. And to do this construction, I need to tell you a quick fact. So conformal nets a priori live on a circle, but you can use them to construct an algebra that you can assign to an arbitrary abstract one manifold. So if I have any one manifold that is not an interval on a circle, I can still make sense of a one-Neumann algebra that I can assign to it. This construction is slightly non-trivial, but it exists. Yes.
For a mortal who only knows CFT, what do you have like any information you could give for what, like how you think about this bicomutant category that assigns to a point?
I will come to it. That I have not said anything about it right now. So, okay. Yes.
Does your construction at the level of the Hitler space reproduce something like the operator state?
At the level of Hilbert space, so at the level of what I assigned to two manifolds, at the level of two manifolds, it should give me conformal blocks. So I'm essentially extending the data of a modular functor. Yeah. Okay. Okay, so now I will spend some time on, because the correct question to ask is, what is this category assigned to the point? What is the flavor of it? So there are different flavors of representation categories of conformal nets. So one of them is very well known. So if I have if I have a Hilbert space with actions of all algebras that are associated to intervals on a circle, which is all intervals that look like red on this image. This is called a representation of a conformal net. You have to basically ensure that the actions restrict well. So the isotony property of algebras restricting also applies to their representations restricting. And this category is well known to be equivalent to the category of DHR endomorphisms. So DHR endomorphisms are endomorphisms of an algebra that are trivial at, so suppose I have an algebra associated to this interval, and I take an endomorphism of an algebra that is identity near both identity at the neighborhood of both the endpoints of this. So this DHR endomorphisms were already discovered in the 70s and 80s, and representation categories of conformal nets are known to be equivalent to DHR endomorphisms. There is also a very,
Sorry.
yes,
Question here. For bimodulate.
you consider endomorphisms of algebras. So, yes.
Question, so I thought the rep category of the component it could be chiral, as we said earlier, so.
What do you mean chiral?
Like, not necessarily the Dirichlet center of anything.
But I'm claiming that it is not a Dirichlet center of a fusion category, it is a Dirichlet center of a very large tensor category. Yes. Okay. It's funny that you call it chiral. But okay, so there is a well-known equivalence of representation categories, which are like where the objects are Hilbert spaces with actions of algebras, and the DHR endomorphism category, where the objects are DHR endomorphisms and morphisms are intertwiners. And there is even a more preliminary, sorry, this is broken. There is a more preliminary equivalence. There is an equivalence between bimodules and endomorphisms. So I can take a general endomorphism of an algebra and twist the L2 of that algebra by this endomorphism, something like A. So I have an endomorphism A to A rho, and I can twist its action on the L2 of that algebra by this rho. So I should write it as L2A twisted by rho. And if this A is what is called type 3, then this is even an equivalence of categories. Then all the bimodules you can have of this algebra essentially come by twisting the L2. Okay. Now, the key thing that was previously not very well known was that you can have a similar equivalence between what are called solitonic representations of conformal nets and left and right localized endomorphisms. So they're slightly weaker than DHR endomorphisms, but you can prove a similar theorem. So solitonic representations are where you have actions of all algebras, but not of the intervals that cross the point 1. So everything on the circle, but the intervals that cross the point 1. You can contain the point 1 at your boundary, but you cannot cross point 1. And again, these were studied back in the 70s and 80s by AQFT people, and they were the one who started calling them solitonic representations, because solitonic sectors are essentially sectors that have at infinity correspond to different vacua. And that is somehow algebraically represented by if you're not allowed to represent the algebra associated to something that is crossing this one point. So one of the key theorems is that this solitonic representation category, which is of the flavor of Hilbert space with actions, is equivalent as a monoidal category to the left or right localized endomorphism. So there are two categories you can write: left localized and right localized. And all three of them are monoidally equivalent to each other. And a further theorem is that the Drinfeld center of this category is rep A. And this is a very strong statement and does not require any assumption on the conformal net. And it even removes something that was previously thought necessary to be strong additivity and so on. So any conformal net that you can think of, you can write this category Sol A, whose Drinfeld center will be rep A. Yeah.
Sorry, I'm gonna ask the same question.
Yeah.
Is there this one interpretation of Sol A? Can I think about it as a category of twisted models?
No. In the case of WCW models, this is of the form representations of the base group. And it is a very large category. So
Do you know what it is for SU2 level 1?
as
SU2.
so I will basically write it as rep of omega SU2 at level 1. And given how hard this category is to write, that is how hard the answer to your question.
Is it possible that is just as subsets has objects labeled as where is that?
No, it's too big.
Can I make a comment? But when we talk about the prelude to the positivity condition of the representation,
Yes.
What's the analog of that when you do the base?
You don't have to a priori, like, this is a theorem that I don't know how to consider because this is a special case to where you had taken your conformal net to be the WZW net corresponding to the loop group. So this is a theorem very special to these, whereas for a general conformal net, when I write sol of A, I don't need to put any positivity assumptions on that. So I could have just written this to be representations of A, G, K for the loop group conformal net, and then I did not have to worry about what is the positivity condition I had to write. Yes. Yes. Yes.
Other than one of the oscillars, I thought the definition of essentially was something like objects and half radius.
Yes.
Is there an analytic condition on the half radius?
The half grading is required to be unitary, that's all. But there is no other condition that is required. Like you just take the Drinfeld center as if you were given a tensor category. Yeah. Okay, so a good thing about these localized endomorphisms is that they don't care how small of an interval they are localized on, which is also a hint as to why you would want to assign it to a point. Because now you are essentially saying I'm assigning something very, very close to a point, and the collar can be as trivial, like I can make the collar as big or small as I want. So that's what I would want to do. So given some points P here, a set of zero manifolds essentially, I can assign this category WP of the solidonic representations. And I have two ways to write it. I can either make each of these points into a circle, like I can embed these into a circle and take the solidonic categories for those, or I can take the left localized or right localized endomorphisms of the algebra assigned to little collars of these points. And this category I will call WP. And I have to now assign something to one manifolds, and I assign the category of AI mod. So I had already told you that given a conformal net, given an arbitrary one manifold, I can make an algebra A of I, and the module category will be A of I. Here. Solitonic representations of the net are essentially representations of algebras on the circle, all algebras that don't contain this point 1. So these blue ones are solitonic.
Can one think that the reason they shouldn't contain the point 1 is because there's like a defect inserted there or something? Or
I mean, that's not how the QFT people thought. They thought solitonic is genuinely things that go to different vacua at infinity. So that is the point is essentially infinity, and you're like not allowed to match your vacuum states at infinity. Okay. So to one manifolds, I assign these module categories A of I mod, and now I have to give actions of WP on MI, and I told you that solitonic representations, especially if they're written in the left localized or right localized form, I can shrink their support and extend them by identity. So this action is essentially just given by precomposition. So this will be of the form of an algebra endomorphism, and I'm going to just precompose and act on this module by that twisted action. And now I have two such module categories, and I already kind of introduced to you a process of categorified confusion. So I take these two module categories, I apply my process of taking a fusion of these two module categories in the function analytic sense, and I recover the module category of I1 union I2 with the actions on the ends being preserved. And this is also compatible with the pointing. So all MI1 is a pointed category in the sense that it arises as an algebra, like a module over some algebra. And the pointing, this process is compatible with the pointings. And now you can ask me, okay, what happens when you actually try to do it on two elbows and create a circle. So if I try to do this process on this shape, I recover A of S mod, which is rep A abs, and what you would have wanted is rep A, but there was a strange abs or L2 sitting here, and this vanishes if you are rational or finite index. So in the rational or finite index case, you indeed recover rep A, but this shows that we have fully extended theories that were not necessarily compact. So even something like Liouville or Virasoro for central charges that make it non-rational, you can still do this partial construction of assigning something to a point and assigning something to one morphisms. But now you will not recover this nice modular tensor category here. You will recover some other category, which will be rep A abs in general. But in the cases you love and care for, this is indeed rep A. Okay, so on two manifolds, I am currently working on what is this construction. The reason why people like being fully extended is that now your generators can be much simpler than pair of pans, because assigning something to pair of pans is essentially knowing all your modular data, whereas now if we are fully extended, we only have to assign things here. And in particular, if I'm not compact or rational, then I will not be able to assign things to disks of certain kind. So I can define I can basically write down partially defined theories. Because it is symmetries conference, I have to mention about the physical interpretation of this category solve. So Brandon Stock yesterday mentioned that if you have a sub-algebra of a VOA, you can consider the same ver V W. I can do the same thing. I can take a sub-conformal net B of the conformal net A, and I can consider the category sol BA. That is solidonic with respect to A, but is a genuine representation of B. So B is a sub-algebra, and I have actions of B for all intervals on the circle, but I don't have actions for rest of the things in A for all intervals on the circle. And what I want to call this thing is B topological defects, because sol AA is essentially rep A. Sorry. And so solidonic, yes.
If you take B to be the Virasoro subnet.
Yes, that's what I've written.
Oh, okay, but then solid A really is like a big category of pussy.
Exactly. And so in sol Virasoro A, that is what is a big category you would care about. But in the VOA line, you will never go to sol CA. You will stop at sol Virasoro A.
Sol is sol CA. Okay.
Yeah. So you have gone even bigger, which the VOA land doesn't a priori allow you to do, but there must be something that you can write analogous, because the Drinfeld center of sol Virasoro A will not recover rep A. But the Drinfeld center of sol A recovers rep A, and that's why the VOA people never had access to this category.
So should you think of sol CA as like not necessarily topological?
Exactly.
But
yeah, I would want to say that, but I don't have enough physical sort of words or examples to be able to say that. So I know that rep A is going to be topological lines in the bulk. I want to call sol of Virasoro or sol BA essentially to be B topological defects for the bulk boundary system A. So like whenever there's an insertion from the algebra B, you are transparent for it. But whenever there's an insertion from something else, there's an obstruction. And now the interpretation for sol CA is something I genuinely don't know. And another interesting thing is that I know the Drinfeld center of sol A is rep A. I can think of it as rep A times rep C, which is just Hill. And in the rational case, Drinfeld center of rep A is rep A times rep A op. So this kind of hints at a formula for Drinfeld center of sol BA. But again, I would want to say it is something like rep A times rep B op, but I don't know if this is going to be true. And the last thing or the hidden mystery in this world is how do you recover the central charge? So given a vertex operator algebra, you have the Virasoro, and you can see the central charge sitting in the when you write the bracket for Virasoro, you see the central charge there. Similarly, in the definition of a conformal net, you had a projective action of diff S1, and the Bott-Thurston co-cycle for that recovers the central charge for you. Given a representation category of a conformal net, you can recover the central charge partially. So you can recover central charge mod A by doing the Gauss sum construction. So if you genuinely had a finite modular tensor category that was finite, you could take the objects, take the twist, write down a formula, and recover some formula for the central charge, which had forgotten a lot about the central charge, but still recovered something. So now you have a category whose Drinfeld center is the category you knew and loved, but a priori, I do not have a way to probe for central charge in this. Homotopy theoretic techniques and physicists' intuition say that they should remember something like central charge mod 24, or maybe all of central charge. We don't know, but I right now don't know how to recover central charge from what I have assigned to the point. And this will be an interesting question, because in the TFT land, you say everything is fully determined by what it assigns to the point. In the chiral CFT world, you can't say everything is fully determined, but maybe the central charge mod, something like 24, will be determined by what is assigned to the point. Yeah, that's it.
Questions?
Yeah.
Why are you choose to categorize from one algebra system of C-star?
So let's see. I mean, there is a trivial answer to this question and a non-trivial answer. Firstly, if I take bound, like if you care about Hilbert spaces and you want to do the same thing that you did to vector spaces, take take endomorphisms of it, you land in the von Neumann algebra land. So you automatically see things of the form B of H. And physicists said they like von Neumann algebras because the bicomutant condition is essentially also a very topological condition. You could put a bunch of operator algebraic topologies on B of H, and von Neumann algebra essentially says that you're complete under all these topologies. That is, all your limit points are included in your algebra. And for that reason, von Neumann algebras came to be interesting for physicists.
Yeah, there are two parts.
Yeah.
We might not necessarily be the first phase is from a common system. You only need to operate out.
I mean, it depends on the perspective. Like in some physicists who do QFT would say you need a Hilbert space, and some people would say you need the operator algebra. So
the second problem is if you have too many limit points, algebra some might not be necessary at time.
yeah, I mean, you could write a C-star analog of this. So you could replace von Neumann algebras by C-star algebras, complete W-star categories by just star categories, like C-linear star categories, and tensor categories by just C-star tensor categories. But then you will also lose access to these things that we have, which was like analogs of inner products and so on. So the good thing about being in this particular land is that you get access to like tools that genuinely look familiar from the study of operator algebras. So this world is very sort of happy to deal with things that are not dualizable or rigid, but still admit involutions.
Question.
Yes.
You said you're still working on the assignment for surfaces.
Yes.
And you mentioned before that the dependency on the complex structure is only in this point.
Yes.
Can you say a little bit more about this?
So the way way I'm thinking about assigning things to two manifolds essentially goes through the VOA route again. So I will build a VOA bundle, take holomorphic sections and so on. So that construction, we know that only projectively depends on the complex structure. Like if I had a moduli space of all surfaces, that is my intuition for saying that only the pointing depends, but I have not computed it, so I can't say for sure. But I can tell you the construction later and we can talk.
So should I think of this pointing as a specific conformal block we pick out of the book?
Yes, the pointing is essentially a specific conformal.
So you give various functions and morphisms to the algebra and say that they're up to categories of modules.
Yes.
What corresponds to the morphisms of modules on the morphisms?
Morphism, so morphisms in the endomorphism categories are intertwiners. So they're algebra elements that intertwine. So something like, so if I have rho from A to A and sigma from A to A, then a morphism little a from rho to sigma would look something, see, okay, this doesn't move. A rho x equals sigma x A for all x in algebra A. So they are intertwiners of this form. So then you can basically say that linear maps of bimodules come from intertwiners like that.
I have a question and a correction to my own statement earlier. The question is, so regarding this C mod something, if you can calculate force conformal blocks, then presumably you have C for at least, right?
Yes, but I have not done anything on two manifolds yet.
Then the correction I wanted to give is, I got excited and said that Sol CA might be conformal but not topological defect, but in the chiral setting, these two things I think are the same. So
yeah, so I think Sol Virasoro A is going to be like topological defects of the bulk boundary system, but I genuinely don't know what kind of things Sol A is supposed to be. But there has to be a physical interpretation of it because I can essentially write an entire hierarchy of things. Like I can write Sol Virasoro A, Sol, like I can even take some subalgebra B to be A fixed points of G and then consider Sol AG of A, and I can have a description for this category essentially too. But yeah, so I would want to know what Sol. I mean, I don't want to assign too much hope to finding a physical interpretation of Soli CA, but there are other interesting things that I can do that anybody who does orbifolding with conformal nets can do.
these things I think are straightforward.
Yeah, exactly. These things have a straightforward interpretation, and these things are also easy to write down. But to write them as like cross-braided things for G, a non-finite, like a genuine Lie group or a compact Lie group is still open, like work in progress. Yes.
You remind me what the rational condition was, and if there's like a physical interpretation.
I mean, there are various ways to understand rational. For I think, what is the best way? I mean, the term rational comes from the central charge being a rational number, but the essentially the representation category is going to be a modular tensor category, and it's going to be like.
But is there like a microscopic reason why?
Why for like?
So like, is there a condition on your microscopic system that will give rise to the rational?
I mean, I don't know what it is at the microscopic level. Like, I don't know, like, I know what it means for a conformal net to be finite index, but so I can say that in terms of algebra, like inclusions of algebras being finite index, and that corresponds to rationality. But I don't know otherwise how to say what is the microscopic condition. But yeah.
Okay, I think we should go to the next speaker. Let's thank Nivedita.
Yeah, cool. But yeah, maybe we can discuss a little bit about the state of operation after.
Yes,
It's,
and also if you have any, because you are the only person who would know anything about defects that are not topological.
Yes.
So that,
Yes. Uh, good. Yeah, that's what we. Okay. No. Very extreme phase, right? Or
It's, yes, or your 5 minute check-in. And we wanted to see.
Okay. Very good. Are you still alive? I think that's your kind of something.
It's like we did. That is, I just don't track. There you go, things that are beyond. Related to kind of. Yeah, I mean.
Okay, so next talk will be by Alison Warman on intrinsic DQCP transitions from twin phases.
Thank you very much. This talk is based on 2 papers written with Warman and Sakura Shakunami, who is our supervisor for operational efficiency. So let's start. Notice that I chose this blue colour theme to remind us all of swimming in the sea or in nice mountain lakes. Okay, so the physical question we wanted to answer in this paper is, are all phase transitions dual to spontaneous symmetry breaking transitions? Indeed, we know from Landau theory that if we have group G, then its gap phases can be labelled by the preserved symmetry subgroups. So, for example, here H1 and H2. Okay, and a phase transition between them is given by a spontaneous symmetry breaking transition. So basically, if one phase preserves the subgroup H1, which is larger, it means that it has fewer ground state degeneracy. Then that there's a particular charged operator that has trivial vacuum expectation value in that phase. And then to drive the phase transition, this particular order parameter gains a valve from going from the gap phase in H1 to the one for H2. So by gaining the valve, it increases the ground state degeneracy, and we have spontaneous symmetry breaking from H1 down to a subgroup H2. However, since the days of Landau, we learned that there are other transitions in which it's not the case that the preserved symmetry is contained in the other one. However, in many cases, the ones which are known before our work in 1+1D, these phase transitions appear beyond Landau in one frame can actually be mapped to Landau transitions by doing a partial engagement of the symmetry. So an example is for Z2 symmetry. So this has a trivial and non-trivial SPT phase, which both preserve the full symmetry group. But Kennedy and Tazaki shows that this can actually be a dual to a symmetry transition between a trivial and a Z2 squared SSB, and they call this hidden symmetry breaking. So this is a transition, a beyond Landau transition in one frame, but it can be gauged to a Landau transition. Another example is if we take again Z2, C2 now with mixed anomaly, by gauging Z2, this can be mapped to a transition between the trivial and Z4 SFT. So, seeing all these examples, the natural question is, are all phase transitions dual to spontaneous symmetry breaking transitions? So if we have some particular type of transition here, there's always exists a dual symmetry in which it becomes like that. Yes?
Are you going to say something about the transition?
Sorry?
What the DBS?
No, because I'm going to focus on 1 plus 1D.
The 1 plus 1.
So I'm going to focus on analogues of each D in 1 plus 1D. Now, in 1 plus 1D, are all phase transitions dual to spontaneous symmetry breaking transitions? The answer is no. So we showed that actually we can have transitions between phases in 1 plus 1D that are not related by gauging to any Landau transitions. And this follows from the existence of twin phases, which have the same number of ground states. So they're a pair of inequivalent phases, for example, here shown preserving symmetry S1 and S2, which are not in a subsymmetry relation, such that the two phases have the same ground state degeneracy. And this same ground state degeneracy is maintained even by doing all possible partial or full gaugings of the symmetry. In particular, twin phases have no relative SSB in any duality frame. This means that any direct and stable transition between twin phases is intrinsically beyond Landau. So it will always be a beyond Landau transition, even after we do these gauges. We will particularly show an example in which the two twin phases preserve inequivalent non-conjugate subgroups. And this will give us intrinsic DQCP transitions. So as I said, here we're using DQCP, so terminology of deconfined quantum critical points that indeed came about in 2 plus 1D for the analogues of this in 1 plus 1D to mean simply a transition between phases that preserve inequivalent subgroups. Okay. I also want to comment that although I'm a physicist, so I will focus on the physics aspect and this application to phase transitions without hidden symmetry breaking, that's very interested in mathematics behind this, because the twin phases actually come from twin algebras, which are condensable algebras with the same underlying object, but inequivalent algebra structures. So hopefully this talk will be interesting both to physicists and also to some mathematicians. So let's see how we can obtain these results by using the CTFT. Now, many of you are very familiar with the CTFT. So if we want to describe the physical symmetry properties of theory T, we can put this theory on the physical boundary and then couple it to background gauge fields, extend them into a D plus 1 dimensional topological bulk, and then introduce dual gauge fields in this bulk. And then we have to fix a particular symmetry by choosing a symmetry boundary. This will then tell us the properties, the symmetry properties of the theory T after we shrink the topological interval. This is useful because it can enable us to do computations in the bulk and then determine all these properties of the phases. So for the symmetry, the CTFT is simply a BF theory, but obviously this has been generalized, and as we've heard also in many talks, both at this conference and in many other previous conferences. So thank you to everyone in the audience who has contributed to this very exciting topic. Now, how do we describe gapped topological phases from the CTFT? We fix a symmetry boundary, which is always topological for our cases, and then we choose also a topological physical boundary. Then the topological lines that can end on both the symmetry and physical boundary will give rise to local operators in the theory. If there's a single one coming from the identity line, we will have a symmetric phase. If we have multiple of them, we will have spontaneous symmetry breaking. And interestingly, so in high dimensions, we can see topological order as an SSB for a higher form symmetry, where the charged lines under the higher form symmetry come from, for example, surfaces ending on both boundaries of the CTFT. But here I will focus on 1 plus 1D, where TQFTs are characterized by their number, a vector, and a symmetry action. where the number of vacuum is given by basically the scalar product of these endpoint coefficients on the symmetry and physical back. Okay. We can also use the SimCFT to construct new phase transitions from known ones by doing a partial condensation. So if we have a condensable algebra A, if we start with the SimCFT for an S symmetry and then we condense A, this will give us a reduced topological order, which is the SimCFT for S prime, for a smaller symmetry. And this will encode a topological interface where the anyons that can end on both the symmetry band, the anyons that can end on this A are condensed. The ones that are non-local cannot go through and are confined on the interface, or the ones that are local with the condensed anyons can go through and will become anyons in the reduced topological order. This is useful because the reduced topological order is always much smaller, and it can enable us to input the known simpler transition for S prime symmetry here, and then map it through this map of anyons to obtain a phase transition for the larger, more complicated symmetry S between S symmetric phases. Okay, now let's come to the more mathematical part of this talk about the twin algebras that would then enable us to construct these twin phases and that Warman phase transitions. Okay, so since there are many mathematicians in the audience, I think it's nice to also give a few mathematical definition terminology. So if we have our fusion category symmetry S, then the topological defects in SimCFT form the Drinker center. And a condensable algebra is, has this mathematical definition, and physically it means that it's an algebra of anyons that can consistently and mutually be condensed. And it's called Lagrangian if it's maximal and give rise to a boundary condition. Now we will focus on 1 plus 1 theories whose symmetry is related by gauging to a finite group G with a possible through-phase cycle. Okay, now how are the condensable algebras in these group theoretical derivative centers characterized? So this is the full algebra classification. So they're labeled by a subgroup, which physically corresponds to the preserved symmetry. Then a normal subgroup N of H, which is basically the symmetry that detects trivial. And that's why the reduced TO is the quantum double of H mod N. So we basically spontaneously break G to H, and then we quotient by N, which is the symmetry acting trivially. Furthermore, on N, like before we quotient by N, we can also stack an N ST. So basically a function gamma that trivializes the anomaly if there's no anomaly, or if it's, I mean, if this is just identically 1, this is an SVT, mathematically a group 2 co-cycle that basically tells us that operators labeled by N form a projective representation. And then there's another bit of data, which is this epsilon, which encodes the charge, basically the H action on N. So if we have this local operator labeled by N and we act by conjugation by H, then it will give us O conjugated by H, but also with this possible phase at. Okay, so this is the data classifying the condensable algebras. And furthermore, there's an equivalence relation on it, which I will not clarify commonly, because importantly, this data is actually redundant. So there is an equivalence relation. And this is important because we want to describe inequivalent phases. So we need to first know clearly when two phases are equivalent. And this happens when the subgroups are related by conjugation and when the algebra data is related as follows. And I just want to comment that this is like non-trivial because, for example, even for an abelian group, like a Z2 cubed, you would expect that conjugation doesn't do anything. But actually, if we have Z2 cubed and type 3 anomaly, the phases that are labeled by a subgroup, which is Z2, Z2, and trivial and non-trivial 2 co-cycle are actually equivalent. They become equivalent because of this term coming from omega, which basically tells us that in the presence of an anomaly, we have some counter term that can identify the 2 SVT. Okay, so now we have our algebras, we have an equivalence relation. We would like to now map them to anyons. Now, the algebra data can be expressed in terms of anyons. And typically in the physics literature, this is what people focus on when discussing condensable algebra. It's just the anion decomposition, which is shown here. And so all this algebra, where we're just labeling it by their anions, can be mapped to its underlying object, which is given by anions, which is labeled by a conjugacy class and the representation of its centralizer with some coefficients, which is computed as follows. This looks complicated, but it's really just taking scalar products of characters. Just if we have a representation of a group and we want to decompose it into reducible representations, where here we have but this is generalization to quantum doubles, where we have the anions that are representations of the quantum double, and this coefficient is the scalar product of the character of the algebra, which is basically epsilon. And we see that, whereas for a group, the character of the representation would be just a function of one group element. Here we have a function of two group elements because it's a quantum double. Okay. And then here on the left-hand side, this is the character of the anion. Basically, we're taking the scalar product, and this gives us the anion decomposition of the algebra, so it gives us the underlying object. Now, interestingly, there can be inequivalent algebras that have the same object, the same anion decomposition, and we call these algebras twin algebras. So, if we write down all this algebra data and then we map them to anions, we can determine if two algebras are inequivalent but have the same anion decomposition. Physically, this is very interesting because it gives rise to twin phases that are the main protagonists of this talk. How do we obtain twin phases from the CTFT? We fix particular symmetry boundary. And then on the physical boundary, we can condense these twin algebras, A, K, where K is 1 or 2, for the two twin algebras. Now, importantly, because these twin algebras have the same anion decomposition, so the same simple anions with the same multiplicities, it means that after we can factor the sensitivity, the two twin phases will always have the same number of ground states. And this means that they have no relative SSB. And this happens even if we change the symmetry boundary, because changing the symmetry boundary does not alter the fact that we have twin algebras on the physical boundary. So this gives us these twin phases that have the same ground state degeneracy for any symmetry. Now, how can we get these twin phases from the algebra data? Like, what are the types of twin phases? Now, remember that there are 4 bits in the algebra data. There are 2 subgroups, H and N, and 2 algebra additional data, analysis data, which are basically 2 cosine gamma, and then the H epsilon and epsilon. Okay, so we have these 4 bits of data, and we can have twin algebras come in from each of these 4 types. So, for example, we can have H-type twins if we have non-conjugate subgroups H, but the same anion decomposition. And this happens when the 2 subgroups H1 and H2 form a Gaussian triple, which means that basically if we take the intersection of them with the conjugacy classes, this has the same number of elements for the conjugacy classes. This is important because remember that the anions are labeled by a conjugacy class and a representation of the groups. So this is why basically the subgroups have to satisfy this property. Then we can also have N-type twins, where H is the same, but N are non-conjugate. We can also have gamma-type twins, and these are actually the cases that were already, the only cases that were already known in the literature, when one considers H and N to be G. So one is looking at G SPT phases, labeled by trivial and non-trivial SPT, which coincide on commuted pairs of group elements. But we also found that we can have these gamma-type twins, even for non-maximal examples for anomalous symmetries. And finally, we can have epsilon-type twins, where all this data, Hn and gamma, is the same, but we have inequivalent epsilons. These give non-maximal twin algebras. Yeah. And these are some of their physical properties. So, as I already stressed, the twin phases always have the same number of ground states. And they maintain the same number of ground states even if we do partial gauges of the symmetry, and that's because simply they have the same energy composition on the physical map. However, they are distinct phases. So mathematically, the algebras are different, and physically, we can detect them using these more sophisticated techniques. For example, using the generalized string order parameters for these twin GSBT phases that differ by 2 cocycles. For twin SSB phases, instead, we can look at different symmetry action or different OPs of local operators. And interestingly, also for twin gapless phases, there are cases in which by condensing the same anyons on the interface, we actually get different mass of anyons across the interface. So condensing two twin non-maximal algebras will give us inequivalent interfaces and inequivalent deconfined anyons. Okay, I will focus mainly on the twin gap phases and the phase transition between them, which can never be gauged to become a Landau transition. Okay, let's now come to some examples. So we did a systematic search of gap, and there are known twin algebras in group theoretical categories for the order of the group less than 32. The first twin algebras occur for groups of order 32. This is a table in the case where we have no free cocycle anomaly. And we see that actually the only case that has Lagrangian algebras here with no anomaly is a group of order 48. However, if we introduce an anomaly, then we get more Lagrangian algebras. For example, this group at order 32 has twin Lagrangian algebras, even with, if we introduce an anomaly. And we see here that we have all different types of twin algebras. And the groups here aren't that large, like orders between 32 and 48. So let's come to some more details about this group GL23 of order 48 that has twin Lagrangian algebras, even with no anomaly. So this group can be written as QN, semi-direct S3, and it has two non-conjugate S3 subgroups. However, if we write the anion composition of the algebras that correspond to gap spaces preserved in these two inequivalent S3 subgroups, we get the same anion decomposition. Okay. Here, row are representations of the group of dimension 3 and 4. A is an order 3 generator of S3, and H is an order 2 generator. Okay, and the two S3 subgroups differ by their order 2 generator. In one case, it's H, and in another case, it's C times H, and C is just basically times 1, it's the central. Okay, so these phases both have 8 ground states for G symmetry, but they preserve inequivalent subgroups. So in one case, they preserve S3(1), in the other case, they preserve S3(2). So generally, they are non-conjugate subgroups. So we can determine that distinct phases by symmetry action. By acting, for example, with this H, in one case, it will be preserved. In the other case, the S3(2), it will be broken and it will commute to ground states. Now, let's also discuss the order parameters. And we see here that the order parameters for these SSB phases are actually different components of the same irrep of the group. So as we see here, there's a 4-dimensional irrep row 4. Now, how do we know what order parameters it gives rise to? Well, basically, we can restrict row 4 to these two subgroups, S3(1) and S3(2), which represent other preserved symmetry in each phase. And we can decompose it into S3 irreps. Now, the components of row 4 that has a verb in the phases is the identity irrep. If it becomes condensed, it becomes trivial, it gains a verb, it becomes equivalent to the identity. But we see from this block decomposition that for the first phase, it's the 1,1 component. For the second phase, it's the 2,2 component. So we see very briefly in this example that the order parameters for twin phases are basically different. In this case, they're different components of the same generalized charge. In this case, it's the same irrep. Okay.
That's not the one you're thinking of. But...
Yeah, so there are actually twin SPT phases, which, as you know very well, can be distinguished by generalized string order parameters. So here I'm talking about SSB phase, okay? So for the twin SBT phases, one can distinguish them by using these generalized twin order parameters instead of by looking at local order parameters.
Right, although, well, I would phrase that a bit differently, but I wanted to ask about, so you have in this case, you have an SSB, so you have multiple ground states. Does like, which component gains of that, does it depend on, like, which ground state you're looking at, or?
So, okay. Oops, sorry. I don't know why I did it. Now, basically, okay, technically, each ground space preserves a subgroup conjugate to S3, okay? But basically, the coset, okay, the ground states are labeled by these cosets. Each of them will preserve a subgroup conjugate to S3. You can see I'm thinking of right action. Okay, that's physically why the phases are labeled by subgroups of conjugacy, because actually you have a multiple ground states that preserve each of them.
Right.
So basically, the ground states in the trivial, like for the trivial coset, preserve exactly like S31 or 2. Then you need to act by conjugation, and that will be the preserved symmetry. Okay, so you also need to like act by conjugation, like you need to act by conjugation on this, but it will always be like the one favors with this 2. So rather than restricting reports like S31, you need to restrict it to the conjugates.
Okay, yeah. But that is still right. Where this one appears in this restriction of that's just the.
Yeah, so let me phrase it again. Now, but basically the point is that here I'm looking at the order parameter for the ground states in the trivial coset, okay, and it's this like 1, 1 or 2, 2 component. To get the order parameter in the ground states in the other coset, you just act by conjugation on the order parameter for the trivial coset. Because they're related to each other by discrete action. So basically, if you commute them up here, then it means that for the expectation value, you conjugate the order parameter inside that. You just move the symmetry action inside that. So it's the order parameter for the other places.
Yeah. Okay, thanks.
In other examples of what's the reason that it happens is that the defects, whatever one things are charged. Can you see that property?
Yeah, we will come to that probably in the next slide. Right here, exactly. So, indeed. Now, if we want to describe the phase transition between them, that's a problem if there's no anomaly. So, if the order parameters don't carry any charge under the other one, if there's no anomaly, it means that there exists a gap space preserving a subgroup H that contains both S3 subgroups. So if we want to describe phase transition, so if we try to describe phase transition between them, we see that it's actually unstable because it can actually, be some perturbations that can become a composition of 2 Landau transitions, where we go from the phase preserving S31 to the phase preserving this larger subgroup H, and then to which, in the case of no anomaly gap phase, and then to the phase preserving S32. So indeed, if we don't have an anomaly, if we don't have any like charges, where one operator carries the charge on the other, then this can actually become a composition of 2 Landau. This is why we introduce an anomaly to describe the phase transition, to obtain a stable direct phase transition. Because if we introduce a mixed anomaly between the 2 subgroups, physically this will mean that the order parameters will carry charge under the other symmetry. And this mixed anomaly implies that the subgroups individually are still non-anomalous and will still give rise to twin gap phases. But this subgroup that contains both of them is now anomalous and does not give rise to a gap phase. So the phase transition between them becomes stable, and it can't be written as composition of 2 Landau transitions because this phase preserved in H is now excluded due to the anomaly. So we will now consider the case of an anomaly. And this is a mixed anomaly between the 2 S3 subgroups. Now we can construct the phase transition by using this club sandwich technique, where we basically do a partial condensation. And we go to a reduced TO, which is the Z2 squared with the mixed anomaly between the 2 Z2s. And we see here that from the Macromanions, this row 4 that was giving us the 2 order parameters, then gets back to 2 different tanyons in Z2 squared, E1 and E2. And basically the conjugacy class of the twin phases for the Z2 part of S3 also splits into M1 and M2 in the C2 squared. So now we can input a phase transition between the Z2 squared omega phases, like and this is like the D2CP in 1 + 1 leads for C2C2 with fixed anomaly, as discussed in the paper by Carolyn and Mike. And now when we map it through the interface, it becomes a twin phase transition. And that's because for Z2C2, E1 and E2, basically the order parameters became these anyons, which on the lattice are basically CCA or CCB, or here CC1 and CC2, then actually get mapped to these two different components of row 4. Okay. Now, interestingly, although this transition, this D2CP transition for Z2 squared with mixed anomaly can be gauged to a Landau transition for Z4 symmetry, if we do this gauging, and then we map it again across the interface, this now becomes, again, a Landau transition, because from the point of view of the full G CTFT, the phases on the physical boundary are twins. So if we do it in this case, we actually get a phase transition between two full SSB phases for a non-invertible symmetry. So here I'd like to comment that it's important to have these basically non-invertible symmetries in order to obtain twin phases, because if we just had abelian groups, then gaugings would still give us abelian groups. So I mean, if we had just simple abelian groups, for example, with no anomaly or with so-called cohomologically trivial anomaly, so if we just had invertible anyons, then gaugings would give back an invertible group symmetry, so there would be no non-invertible symmetry. And for an invertible symmetry, there's only one full SSB phase. So if we have an invertible group symmetry, there's only one full SSB phase, which is basically labeled by the subgroup 1. So each and is given by basically we have order G vector. Instead for non-invertible symmetries, we can have multiple full SSB phases. And this is what happens if we take one of the twin algebras to be on the symmetry boundary of the CTFT. Okay. So we can also write the lattice model for this. So okay, here we have an anomalous symmetry, but in the lattice model we have basically disordering operators for the preserved symmetry and ordering operators for the spontaneously broken symmetry. We are spontaneously breaking it, so in the lattice we actually have ZZ. Okay, so this is still symmetric. And as we see here, explicitly on the lattice, this is the 1-1 component of row 4, and this is the 2-2 component of row 4. Okay, so we can write this explicitly in the lattice model. And this is the interpolation between the two gapped phases at lambda equals 0 and lambda equals 1, with the transition, this intrinsic D2CP occurring at lambda equals 1. I don't know if the transition is continuous. So, okay, from the CTFT construction, we actually input a continuous transition for this in 2C2. But like, yeah, from the lattice model, basically, yeah, okay, what happens is we have a preserved S3, the preserved S3 has a Z3 subgroup here, which is the same in both phases. So this Z3 doesn't really take part in the transition, it remains frozen to its plus state. So the transition effectively is the Z2, Z2CP transition between the two phases with Z2, Z2. This is like, so the effective, the gapless part of this transition is the one for the Z2, Z2. This is basically what this top sandwich is telling us, that because the Z3, here this N subgroup is common in both phases, and it's preserved in both phases, across the transition, like in both gap phases, the Z3 futrix will basically be frozen to its plus state. So the effective transition acts on basically the qubits for the Z2, Z2s. So effectively, it's in the same universality class as this Z2 squared and mixed anomaly. So for example, like the compact basis. Yeah, so this was actually constructed from the anion chain, from taking the. Okay, so we haven't verified it numerically, right? They came to do a numerical analysis, but like we wrote the gap, like the exact lattice models for the gap phases, and we did we wrote the interpolation between them for the phase transition. But effectively, what happens is that the tutoring part is frozen, and the effective transition is to No, okay, because we did it like from this, like we did it previously, like we didn't just write the status model, like we derived it from these algebra considerations, and CFT is telling us that this reduced TO would lead to a mixed anomaly. And this analysis, this continuum analysis, then translates into the last. Yeah.
That's something.
Yes. But this analysis, yeah, I agree. In general, like if you take two random gap phases, that could be the first sort of transition. But here, we're using this, like, this is telling us that it becomes the C2 squared type 2, for which we know there is actually a continuous CP transition. So that's why I'm saying that, yeah, okay.
Well, there
But
is, but
it would be
have to
nice.
be. So are you saying that any transition with this type of mixed anomaly, like it has to be continuous? Or
No, I agree. It could depend on
right,
the
okay,
of the last model.
right, it could be.
Yeah, I mean,
no, I think that's
yeah, yes, plan on doing the numeric, you know what I mean, roughly to, you know, to verify it, so numeric. I'm saying that this is derived from the continuum analysis, but like from the continuum, the idea is that you then input the Z2, Z2 omega, but as I said, in the lattice model, it's because this the tutrix is frozen and it's effectively Z2, Z2, so it's in the same, like effectively, it's that, you know, Z2, Z2 is like 2 BCP transition. However, when we map it back across the interface, this actually becomes a twin transition that can't be engaged to a number. So I'll just mention that there are other examples. And like I said, if we introduce an anomaly, the first, actually, the smallest order of the group is 32. That's a mixed twin algebras. And with an anomaly, this group of order 32 has twin Lagrangian algebras, has actually many twin algebras here. The Lagrangians are these ones at the two extremes, but then we see that there are many, that all these, like we have lots of pairs of algebras, so the twin algebras also here, and so these are. Now, if we want to describe the phase transition now between the two twin Lagrangian algebras, yeah, actually the reduced Q, so as you can see from this test diagraph that it goes through this algebra A3. And if we compute the reduced TO of A3, it's actually C2 cubed with type 3 anomaly. So the transition is actually a bit more complicated than the case, but it's again an intrinsic like DTCP transition. Now effectively it's in the universality class of this like C2 cubed with type 3 anomaly, which one can obtain, for example, from CFT by taking 2 copies of the compact boson, which have type 3 anomaly, but we need 2 copies to cancel the type 2. Whereas in the previous example, we could just have 1 copy of the compact boson because we wanted a type 2 anomaly between momentum and 1. Okay, so in summary, we're seeing that one has that according to Landau theory, continuous the phase transitions only between cases in which one subgroup is larger than it contains the other one, and they're driven by another parameter that is as trivial vacuum expectation value in one phase and then gains about across the transition and increases the ground state degeneracy, i.e. the spontaneous symmetry breaking pattern. However, the twin phases, this is never the case because they always have the same ground state degeneracy. So if we have direct to stable phase transitions between them, these are intrinsically beyond Landau. So they're beyond Landau one frame, but also in all other symmetry frames related to the initial one by nature. And this is because the twin phases have no relative necessity. Now, there are many possible generalizations and extensions of this, in particular for non-group theoretical categories or even group theoretical categories in higher dimensions. This has some mathematical difficulties for the precise definitions and the equivalence relations and mathematical objects. Then, as we heard, so it would be nice, I mean, it would be quite nice also to describe and to determine whether there are twin algebras and twin phases, the non-group theoretical future categories, even one possibility, in which the full algebraic classification isn't really well known, even in the maths literature. Another question is indeed analysing in more detail the numerical signatures in the lattice models to verify that that exact particular lattice model that, as I said, we derived from this continuum analysis, that it really does describe its second order phase transition to confirm so numerically. You know, we could expect this from the continuum analysis, but indeed one can also substantiate it by doing numerical analysis. And finally, we've seen that spontaneous symmetry breaking is not the full answer to the question of symmetry break to phase transitions. So what is the general theory of the phase transitions? And this is something we are now thinking about. Thank you very much.
Questions? Well, something I'm not fully understand is if I look at the page when I influence like hey, that's always the algebra by adding this big what like the two put diagram my group and use that to stretch the math.
Yeah, so if you consider two phases that typically the two phases that are labeled by subgroup H and two different two co-cycles will have different annual decompositions. So for example, if you consider the C2C2, in one case, like for the trivial phase, it's purely magnetic algebra. So the anyons are just the magnetic anyons, the ones labeled by pure group elements. Instead, in the non-trivial SPT phase, that magnetic pairs are ions. So they're ionic anyons with the group elements and the representation. So you actually have different annual decompositions, for example. It's only for very specific two co-cycles in which you get the same annual decomposition. So you get to wait out. Typically, I agree. So if you have the two co-cycles, if you have this same group but different two co-cycles, these will preserve the same symmetries. But differently, they will have different annual decompositions. So you can disengaging semantics to a Landau transition is done by Canadian sub species C2C2 trivial and SST phase, and it can actually gauge the trivial C2C2 SST phase because it's different, like the different annual decomposition object.
So let's say you have a quantum double and between Lagrangian algebra. So there are two non-isomorphic S algebras, but the same objects.
Yeah.
So whether the module category of the Lagrangian algebra monoidally equivalent, like they are not equivalent as monoidal modules of your quantum double, but whether they are monoidal equivalent.
Yeah, so from the point of view of classifying the condensable algebras, the subgroups are labeled by conjugation. Okay. Now, we're not, okay. And there's actually basically a one-to-one correspondence between the Lagrangian algebras and the module categories. So like in our cases where they preserve the non-conjugate subgroups, the module categories would again be labeled by non-conjugate subgroups. So they will also be in equivalent. Because I mean the module categories are labeled by basically the Frobenius algebra in the category of Asia, which is again labeled by the subgroup. So if the groups are non-conjugate, the Frobenius algebra is
I kind of have a comment to that, which is the module categories, of course, are inequivalent as module categories, but you can sometimes have that for twin algebras, there are corresponding, two module categories, right, which kind of carry just different like nimreps of the fusion category actually. So you can see it actually like, so this is like, if you have 10 algebras, then in some sense, like the anion decomposition is giving away the gauge invariant information, right? And so it's hard to detect that on that side, but on the module category side, the NIMREFs, which are the gauge invariant information, you can detect it over there. But this is not always the case. They're very
Yeah, then just another quick comment that, yeah, if you have like these SSB phases, there's one phase, which is the thermodynamic phase of the ground phase, labeled by the COPA, in which they have an equivalent symmetry, so equivalent symmetry action, as I said. However, one can also do a change of phase to one ground state to fix the same symmetry action in both phases. But if you do that, then the OPs of local operators become an equivalent. So we, in an SSB case, you have a ground state regeneracy, so you can just take these linear combinations, you can actually fix the same symmetry, but you will still see that they're different in equivalent phases by the OPs.
Did I understand correctly that you actually have a candidate for the critical? And
So we have candidates
you
for.
tell me about criticals on safety. Do you actually know what the critical is?
Yeah, so as I said, like, okay, so our transition is actually a gapless SSB phase. So it's like multiple copies of, so if it's that there's an SSB plot, it's a CFT tensored with some SSB. Because both ground states, like this is a transition between SSB phases, and there's some symmetry which remains SSB in both of them. So the gapless phase will actually have still some SSB, and then which is the gapless sector, and then it will have the gapless sector, which from the sensitivity analysis is like in the same universality class as compact boson. The transition between Z2, Z2 with type 2 anomaly phases preserving an equivalent subgroups. Yeah, so this is like from what we get from the continuum sensitivity analysis, but I agree it would be nice to also confirm it numerically for the last.
Yeah.
No, okay, sorry.
So we know the critical point because we know the relevant operator.
Yeah, exactly. Yes. We know the relative operators. That's sorry. They're basically these two Z2. Yeah. So the operators, sorry, are like ZJ, J plus 1 for row 4. So you can write these very explicitly. These are generalizations of the Z2E, but here we have the representation row, components MN. And then so you can write these matrices and then just take the products of matrices and then the components 1, 1. This is the order parameter for one phase, and this is the order parameter for the other phase. Okay, here I took like the interpolation of the two Hamiltonians, one with 1 minus lambda, one with lambda. So this is the order parameter for one phase, and this is the order parameter for the other.
Other questions? Okay, let's thank Alison again.
It's like the ground state is not, not about the choice of ground. It doesn't have the same component. Also like the trivial record.